All right, class. Good morning. I apologize for starting a little bit early today, um, but I have a science department meeting at 1 o'clock, and so I wanted to get it done. And plus, it's just getting too hot in the afternoon, and I don't really feel like doing anything in the afternoon. So I've been trying to wake up earlier, get my exercise in, do this, etc. Um, Man, if you want to hear something morbid, uh, I I live right next to Hillcrest, which is a senior living facility, and uh, it's a senior living facility, and so whenever there's an ambulance, um, hey spicy pepper, so whenever so basically and then the police station, the Laverne police station, is also right by my house. So what happens is ambulances are departing the police station all the time, and more times than not, they're going to Hillcrest. So it's like I hear an ambulance, and probably 7 times out of 10, that ambulance is headed right past my house towards Hillcrest, and I think it's really morbid. It's like they have like at least one ambulance per day, sometimes two ambulances a day or three ambulances a day, and yeah. So, hey Ben, thanks for joining. I appreciate your commitment to learning. Actually, all four of you, I appreciate your commitment to learning. All right, so today I have May 2018, time zone 2. So, and we're going to do the even, or I'm going to do the even problems, and you guys are going to do the odd problems. Okay? So, all right. So the number 2, it says the velocities Vx and Vy of two boats are shown. Which arrow represents the direction of the vector Vx minus Vy? So what I would do is I would say, all right, so this is going to draw on your knowledge of vectors. Vx minus Vy is really Vx plus the vector minus Vy. So what does the vector minus Vy look like? It's the vector that is the same length but opposite direction. So minus Vy looks, I'm going to take Vy and I'm going to draw a vector that's in the same same length but opposite direction. Okay? So that is the vector minus Vy. Okay? That's minus Vy. And so, and you see that I've drawn it so that it chains into Vx, because when I add two vectors, we want to chain them together and draw the arrow that goes from the beginning of the chain to the end of the chain. So if the beginning of the chain is right here, then the end of the chain is right here. So that would be the answer D, because that arrow goes to the right. Okay. Question 4. A box is accelerated to the right across rough ground by a horizontal force F sub A. The force of friction is F sub F. The weight of the box is F sub G, and the normal force is F sub N. Which is the free body diagram for this situation? Wow, this is a really easy problem. So we have gravity going down, we have normal force going up. Option A doesn't even have normal force. So that one's out. Whoa, that was too extreme. Didn't mean to do that. Option A is out. Option B has no gravity. B is out. Option C has all the four forces in the correct directions, but notice how it says the box is accelerated to the right. So that means that there's going to be an imbalance of forces, and option C has equal up and down forces and equal left and right forces. So that one is out. That option D has the applied force larger than the frictional force, so that means it's going to accelerate. So D is the answer. Question 6, looks like we got projectile motion. The ball of mass m is thrown with an initial speed u at an angle theta to the horizontal as shown. Q is the highest point of the motion. Air resistance is negligible. What is the momentum of the ball at Q? What I would say is Vx initial is going to be u cosine of theta, right? The horizontal part of the motion would be the adjacent part of the triangle, which is cosine. Vy initial is u times sine of theta. So, but what happens is, as the ball rises, the y component of the velocity is reduced by gravity, okay? At the highest point, the y component of the velocity is 0. So we have no y velocity. Okay? However, gravity does not pull things horizontally, so the x velocity remains constant the entire time. So actually the velocity at point Q would be u times cosine. All right? Because the y velocity went away and all we're left with is the x velocity, which it didn't change from the very beginning. And then momentum is mv, so that's just going to be m times the velocity at point Q, which is u cosine theta. So the answer would be B. Question 8. Weight W is tied to a trolley of mass m by a light string passing over a frictionless pulley. The trolley has an acceleration a on a frictionless table. The acceleration due to gravity is g. What is W? So, if we think about this problem, two of the answers don't even make sense whatsoever, okay? Because you can see that this has units that are mass. See how it's mass times an acceleration over an acceleration? So that means that the units of that would be mass. What are the units of weight? They're newtons, okay? So both of these options don't even have the right units. So even if you knew nothing about how to solve this problem, okay? Okay? Even if you knew nothing about how to solve this problem, but you knew about units, you could have a 50-50 chance of getting the answer correct, okay? So it's got to be A or B. Now I'm going to say, well, gee, what if the acceleration was gravity? Okay. what would it mean if the acceleration was equal to gravity? What if the trolley was being pulled to the right with an acceleration equal to gravity? Well, wouldn't that mean that the trolley was very, very light? Okay. So if the acceleration is equal to gravity, then we know that the mass of the trolley has to be really, really light. Okay, so that's another clue. But let me just draw some free body diagrams here. So this trolley, it has a tension going this way. Whoops. Has a tension pulling it that way. And it's got, so basically that tension is equal to the mass of the trolley times A. All right? But if we look at the hanging weight has tension going up, and it's the same tension because it's the same rope. And then we have the weight force going down. All right. So if we were to do Newton's second law for the hanging weight, we would have W minus tension is equal to W over G, which would be the mass, times A. And then we want to add these two equations together. If we add the two equations together, we get W equals M plus, well, you get MA plus W over G times A. We can multiply both sides by G. WG equals MGA plus WA, and then subtract it over. W times the quantity G minus A equals MGA. W equals MGA over G minus A. So that means that the answer would be A. All right. So let me give you kind of a hand-wavy way to get that. So again, notice how this problem, if you go through all the math, it takes a little bit of time. If you notice that two of the answers don't even have the correct units, then you can have a 50-50 chance for guessing. And another thing you want to consider is limiting cases, okay? So if the acceleration of the trolley were equal to gravity, so if A were equal to G, it would have to be an extremely light trolley. The trolley provides no resistance whatsoever to the weight falling, okay? So basically, if acceleration equals G, we would have to have M equals 0, okay? And option A says this. Why? Because if I set the gravity equal to acceleration here, see how the denominator is 0? So the only way to get a weight that isn't infinity is to have the mass equal to 0. So that means that M has to be 0. So see how that makes sense? All right. Number 10, which is a unit of force? Well, I would say work equals force times distance. And so that means that force equals work over distance. So that means that units of force equals units of work divided by units of distance, which means units of force equals joules over meters. So that would be option B. Okay, so I'm a third of the way through. Let me check for questions. Any questions? Who's Asbestos Phlegon? Haven't heard of that person before. Hey Christian. Hey Jackson. Hey Diego. Hey Asbestos. So the SL final is probably going to be more like paper 2. So this review is mainly, so it's going to be, I might throw a few multiple choice on there. Yeah, you can expect a few multiple choice, but the final is going to be quite short. So I'm not going to do a full IB exam, because a full IB exam takes like 3 hours. I don't want to do that. Oh, it's Katie. All right. So going on to number 12. A container that contains a fixed mass of ideal gas is at rest on a truck. The truck now moves away horizontally at a constant velocity. What is the change, if any, in the internal energy of the gas? And what is the change in any, if any, in the temperature of the gas if the truck has been traveling for some time? Okay, so I think this is a horrible question. This is such a horrible question because it depends on what you consider. Okay. All right. So, for example, what if I consider the effects of air resistance? Okay. Air resistance is going to, basically, if you have airplanes, for example, the wings of an airplane actually heat up because air resistance generates heat. Okay. So if this truck is going fast enough where air resistance is going to play a factor, then the truck is going to heat up, which means that the ideal gas that's in the container is going to heat up, which means its internal energy is going to increase, which means that its temperature is going to increase. So if I think about things that way, I would say the answer is D. However, here's what I think they're getting at. I think they're trying to get at internal energy is the random kinetic and potential energy of a thing, okay? So the fact that it's moving doesn't mean that its internal energy has changed, because the motion of the truck is a coherent motion. It's not random, okay? So I would say, I think that the answer is A, where it's going to say that the random internal energy, the random kinetic energy are unchanged, which means temperature and internal energy are unchanged. But you can look up in the key whether A was the right answer or not. But I think this is a bad question, so I'm going to give it a frowny face. All right, question 14. Two sound waves from a point source on the ground travel through the ground to a detector. The speed of one wave is blah, the speed of the other wave is blah. The waves arrive 15 seconds apart. What is the distance from the point source to the detector? Oh, here comes the ambulance. So, velocity equals distance over time, because waves are traveling at a constant speed. That means that distance, or distance equals velocity times time. And both of these waves are traveling the same distance because they're traveling, it's basically an earthquake wave. So we have basically V1 times time 1. Here comes the fire truck. Equals V2 times time 2. All right? We know that the slower wave, so V1 we know that the slower wave took 15 seconds longer. So T2 is equal to T1 plus 15. So now I'm going to plug in the velocities. I have 7.5 times T1 equals 5 times T1 plus 15. All right. So that tells me that 2.5 T1 is equal to 75. All right, and 75 divided by 2.5 is going to be what? 30. So T1 equals 30 seconds. And that means since VT equals distance, that means that, well, we know that the velocity of wave 1 was 7.5, and the time was 30. So 30 times 7.5 is a little over 210, so the answer must be D. All right. Number 16, what are the changes in the speed and wavelength of monochromatic light when it passes from water to air? So water is a slow medium, okay? And so if you go from water to air, the speed is going to increase. So it's got to be A or B. It's got to be one of those two. Now, one of the things I taught you was that the frequency of the wave is independent of the medium, okay? As long as the wave, it's the same wave traveling, the frequency stays the same. So wavelength, which is lambda, is speed over frequency. The frequency is constant. So we can see that if the velocity goes up, like it does when it goes from water to air, the lambda has to go up. So the wavelength also has to increase. So the answer is A. 18, a pair of slits in the double slit experiment are illuminated with monochromatic light of wavelength 480 nanometers. The slits are separated by 1 millimeter. What is the separation of the fringes when observed at a distance of 2 meters from the slits? Okay. So let me draw this out. We have two sources, and they're separated by 1 millimeter. Okay. And then you have a screen over here, and that distance, this horizontal distance is 2 meters. Okay? Wow, this is a horrible drawing. You know what? I'm just going to do this. I'm just going to go to the equation. There's an equation in your textbook which says that basically, I'm blanking on the equation. Why am I blanking on the equation? It's going to come to me in a second here. I'm going to come back to number 18. Number 20. An electron enters the region between two charged parallel plates, initially moving parallel to the plates. The electromagnetic force acting on the electron. So if we think about these charged plates, this has like maybe positive charge, and maybe this one has negative charge. Okay, so we're going to have an electric field that's going vertically. Whether it's going up or down doesn't matter. So basically this electron, when it enters the region between the plates, it's going to get pushed up or down. Okay? It's not going to get pushed side to side. So the horizontal speed of the electron is going to remain constant. And then the vertical speed is going to be changed. So the electromagnetic force acting on the electron is going to cause the electron to is parallel to the field lines and in the direction opposite to them. So that would be the answer. The force is going to push the electron up or down. All right, number 22. The cell has an EMF of 4 volts and an internal resistance of 2 ohms. The ideal voltmeter reads 3.2 volts. Notice how the ideal voltmeter is connected across the external resistance. So that means that the terminal voltage is 3.2 volts. Okay. So notice how the EMF is going to be, the EMF is 4 volts. Okay. So if the terminal voltage is 3.2 and the EMF is 4, then that means that the voltage drop across the internal resistance is equal to 4 minus 3.2, which is going to be 0.8 volts. Okay? So the internal resistance, so then we use V equals IR. So the internal resistance gets a voltage drop of 0.8 volts, and it has a resistance of 2. So that means the current that is flowing in this circuit is 0.4 amps. That current then flows through the external resistance because it's a series circuit, so the current that the internal resistance gets is the same as the external resistance. And so V equals IR again, only this time for the external resistance. We know that the terminal voltage is the voltage that the external resistance gets. That was 3.2. And then we know that the current was 0.4. So we can solve for the external resistance, and it looks like it's going to be 8 ohms. So the answer is D. 24. A detector placed close to a radioactive source detects an activity. Activity means decay rate of 260 becquerel. Becquerel is the unit of decay rate. The average background activity in this location is 20 becquerel. The radioactive nuclei has a half-life of 9 hours. What is the activity detected after 36 hours? So when they say background activity, what they mean is that we're being hit by radioactive particles all the time. Concrete, for example, is slightly radioactive. So there's always, and then we're getting hit with radiation from space. The sun emits radiation. So there's always a background. So if we look at it, the activity due to the source initially is equal to 260 minus the background. So it's 240 becquerel. Then we have the half-life is 9 hours. And we want to know what is the activity after 36 hours. Okay. And so that would be 4 half-lives. So 4 half-lives is going to reduce the activity by 2 to the 4th power, which is 16. Okay. So the activity due to the source after 4 lambda is going to be 240 divided by 16, which is going to equal what? 15 becquerel. Okay. And but here's the thing: the detector is always going to pick up the background radiation. So we have to add back in the background radiation, so we get 35 becquerel. Because the detector doesn't know what's coming from the source and what's coming from the background. Background radiation is more or less constant. It could change based on things like location. If you move close to concrete, you're going to have more background. If you move up in elevation, you're going to have more background because there's less atmosphere blocking the radiation from space. But I would say the answer is D there. Okay. A graph of the variation of average binding energy per nucleon with nucleon number has a maximum. What is indicated by the region around the maximum? So let me draw what the graph looks like. Yeah, that's kind of what it looks like. Okay, so there's the X and Y axes. And the graph kind of does this. It goes like this. Okay? So there's a maximum right here. And that maximum is iron. Iron has the highest binding energy per nucleon. So if you have the highest binding energy per nucleon, then that's where you have basically the most stable nuclei. So I would say the answer is C. 28. A wind turbine has power output P when the wind speed is V. The efficiency of the wind turbine does not change. What is the wind speed when the power output is P over 2? So we learned an equation for the power output of a wind turbine. It is power equals epsilon times 1/2 rho, which is the density of air, times the area of the blades times V cubed. So notice how epsilon, rho, and area are all staying the same if we change the speed. So if we want the power to go to 1/2, notice how we have to cube 1/2, or we have to cube something and have it, once it's cubed, it's equal to 1/2. You get what I'm saying? So it's got to be d, because d has the cube root of 1/2. So because when we cube the cube root, we get 1/2. 30. Ooh, I got a package. Should I open up the package? I'm going to do it. This is an unboxing here. Woo-hoo-hoo! Oh yeah! I heard this game is fun. Have you guys heard of this game before? I'm going to play it. Dominion. All right. So back to question 30. Mars and Earth act as black bodies. Power radiated by Mars divided by power radiated by Earth equals P. And the absolute mean temperature of the surface of Mars is divided by the absolute mean temperature of the surface of Earth is T. What is the value of the radius of Mars divided by radius of Earth? Okay. So basically, what we learned in equation, it's power radiated equals sigma a t to the fourth. Okay, so we're going to write one of these equations for Mars. Okay. And sigma doesn't need a subscript for Mars because it is a universal constant. And then we have for Earth, we have sigma a of Earth times t to the Earth to the fourth. So this is the Stefan-Boltzmann law. And we're going to take the ratio of these two equations. So we have P Mars divided by P Earth. The sigmas cancel out. A Mars. And remember, you know what? I'm going to write this in a different way. Area is 4 pi r squared. Okay? So I'm going to write it as that, 4 pi r squared. So taking the ratio, notice how the sigmas and the 4 pi's cancel out. We get Rm over Re squared, Tm over Te to the fourth. Okay? So Pm over Pe is just what they called P. So P equals Rm over Re squared. And then the ratio of the temperatures is T. But keep in mind that's raised to the fourth power. So that means that Rm over Re squared equals P over T to the fourth, which I then have to square root. So I get Rm over Re equals P to the 1/2 over T squared. So that would be B. That was a tricky one. All right, going back to the question I missed. Where is it? Number 18. So you guys might remember that equation where I said that if delta R equals n lambda, then that means it's constructive interference. So when we say the separation of the fringes, basically we mean that n equals 1 because the difference, okay? So what is delta R then? It turns out that there's an expression for delta R, which I'm not going to go into, but delta R is dy over L. Okay, where D is the separation between the fringes, between the sources, excuse me. Y is the separation between the fringes, and L is the distance between the sources and the screen. So this is going to allow us to solve for Y. We're trying to solve for Y. Y equals lambda L over D. It says that lambda is 480 nanometers, so 480 times 10 to the minus 9. L is 2 meters, and D is 1 millimeter, which is 1 times 10 to the minus 3. So I can plug that into the calculator. 480 times 10 to the minus 9 times 2 over 10 to the minus 3 gives 9.6 times 10 to the minus 4 meters, which would be D. Okay? All right. So let me see if I have any questions. It was not the knife making kit. It was a board game. Christian asks, is the work for this quiz this week or next? So the practice problems you're doing this week, you're going to submit those as next week's quiz. All right? So that's all I have for today. Have a great weekend.